have you ever built an app and you know that feeling, right? It works perfectly on your machine, it's super snappy, but then it just grinds to a halt under real-world load. Today, we're going to dig into the concept that explains exactly why that happens and, more importantly, how you can prevent it. We're talking about bigO notation. I mean, it's the classic story. You build something, a few friends use it, everything's great. Then you launch, your user base starts to grow, and suddenly, performance just tanks. Well, look, this isn't just bad luck. It's actually a problem of what we call algorithmic complexity, and it's something we can totally predict and solve. The key to cracking this whole scaling problem is bigO notation. Now, don't let the name scare you off. Seriously, it's not just some abstract math thing. Think of it as a practical language, a way to describe how your code's performance is going to change as your data grows. Okay, so to really wrap our heads around what bigO is, we've got to start with what it isn't. And a super common misconception, like the one from this online discussion, is that it's all about just counting lines of code or maybe the number of instructions the CPU has to run. Yeah, that's just completely missing the point. bigO isn't about counting every little specific instruction. It's about seeing the bigger picture of performance. So what is it then? Well, bigO describes how the runtime or even the memory usage of an algorithm grows as its input size, which we just call n, gets bigger. It's all about the trend line, the growth curve, not a specific time on a stopwatch. And I love this quote from another developer because it just nails it. An algorithm with a great bigO might actually be slow for a tiny input, and one with a terrible bigO might be fast for that same tiny input. But bigO doesn't care about that. It cares about how that speed changes when you go from 10 users to 10,000. So let's break this down. What bigO is a way to talk about how runtime grows. It lets us compare the fundamental scalability of two different approaches. It's about the shape of that performance curve. What it isn't is a stopwatch. It's not about raw speed in seconds, and it's definitely not a perfect crystal ball for real-world performance. All right, now that we've got the basics down, let's go on a little tour. We're going to look at the most common bigO complexities, starting with the absolute best and going all the way to the catastrophically bad. This is going to help you build an intuition for spotting these in your own work. And to make this super easy to understand, we're going to use this great analogy from a Reddit user. Just imagine we need to find one specific pen in a classroom that has n students. The way we decide to search for it is going to define our bigO complexity. First up, the holy grail, O of 1, or constant time. In our classroom, this is like you know exactly which student has the pen. You just walk up to them and get it. It doesn't matter if there are 10 students or 10,000 students in the room, the amount of work you do is exactly the same. That's why the graph is just a perfectly flat line. All right, next up, we have O log n, or logarithmic time. And this one is super efficient. In our classroom, this is like playing a guessing game. You shout, "Is the pen on the left side of the room?" And with that one question, you've just eliminated half the students. You take the group that's left and you do it again. So even if the number of students doubles, it only takes one extra step to find that pen. The growth is incredibly slow. Okay, so from there we get to O of n, or linear time. And this is probably the one that makes the most sense right off the bat. This is where you go to every single student, one by one, and ask, "Hey, do you have the pen?" The work grows in a perfect one-to-one relationship with the number of students. You double the students, you double the work. Simple as that. Now, this is where things start to get painful. O(n squared, or quadratic time. This happens when, for every single item you're looking at, you have to do something with every other item. In our classroom, this is like asking every student about every other student. So for 10 students, that's 100 questions. For 100 students, that's 10,000 questions. You can see how this explosive growth, which usually comes from nested loops, makes that performance curve just skyrocket. And finally, we get to the really, really horrible end of the spectrum, O of n, or factorial time. This is basically a computational cliff. In our analogy, this would be like trying to find the pen by checking every single possible seating arrangement of all the students in the room. The work just explodes. I mean, look at this fact. For input size of just around 60, the number of operations you'd have to do is more than the estimated number of atoms in the entire known universe. Yeah, you want to avoid this one. And wow, just look at the difference here. On the left, in green, you see that gentle, manageable growth of an excellent logarithmic algorithm. And on the right, in red, that is the sheer cliff face of a horrible factorial one. This visual contrast is exactly what bigO helps us understand before our servers start to melt down.
Okay, so that's the theory. But how do you actually use this stuff? Like, how do you spot these complexities in your own code? Well, there are a few really simple rules of thumb you can use. There are really just 3 simple rules to keep in mind. First, constants don't matter. So whether a loop runs n times or 2n times, the growth is still linear. We just call it O of n. Second, the fastest going part is all that matters. If you have an O of n squared operation and an O of n operation, the whole thing is just O n squared, because that's the part that's going to take over when n gets big. And third, nested loops multiply. A loop inside of another loop gives you n times n, which is O of n squared.
Let's take a classic example, sorting a list. As you can see here, different ways of doing the exact same task can have wildly different complexities. Simple approaches like bubble sort are O of n squared, but really clever algorithms like quicksort and merge sort get you down to O of n log n. This is way, way more scalable than O of n squared, and it's a perfect example of why choosing the right algorithm for the job is so important. Okay, but now we have to talk about a really important point, the real world. bigO is an incredibly powerful model, but it is just that, a model. It's an abstraction, and sometimes the details that it leaves out, well, they really matter. And I love this quote from a developer online because it's a little provocative, but it makes a great point. The hardware we're running our code on today has changed a lot since bigO was first thought up. Modern CPUs are these incredibly complex beasts, and just counting operations doesn't always tell the whole story. You know, things like how your CPU caches data, the way your code accesses RAM, even how the processor tries to predict what your code will do next, all of these can have a massive impact on actual speed. This is exactly why 2 algorithms that are both technically O of n might have totally different runtimes in the real world. One might be cache-friendly, making it way faster in practice, and bigO just doesn't capture that level of detail.
So here's the bottom line, the big takeaway. bigO isn't broken. It's just not the whole picture. Its main job, and it's an incredibly valuable one, is to be a first-pass filter. It helps you throw out the ideas that are fundamentally unscalable, those O(n) squared or O(n) factorial algorithms, and it guides you towards solutions that actually have a fighting chance as your data starts to grow. And that's really what it all boils down to. You now have this language of growth to describe and predict how things will scale. So the question I'll leave you with is this: what happens when you start looking at your own projects through this lens? Where are those hidden O of square loops, those little performance time bombs just waiting for your user base to get a little bit bigger? Thanks for tuning in.